Wednesday, we talked about algebraic proofs, and we went through a bunch of properties like the addition property, subtraction property, multiplication property. We're still going to use a lot of those properties as we start getting into geometric proofs. Okay? We're still going to be looking at equations. Okay? We're just going to be talking about segments and angles and triangles now. Okay? But we're still going to be able to add things to both sides of an equation. Now, what we looked at with these properties was things that were equal to each other. Okay? It says right here, the properties above may only be used with equal signs. Today we're going to start looking at properties of congruence. Okay? So it's important to make the distinction, okay, when we're talking about segments. Okay? Segments are what we are going to be talking about today. You can make a little note. Lengths are equal to each other, right? So if I'm talking about the length of a segment, right, that's like a numerical value. I can say this segment is 10 centimeters long, right? So I can say that lengths of segments are equal to each other. But when I talk about the actual segment itself, right, the geometric figure, okay, so we can say that lengths are equal, segments are congruent. All right? So the lengths of segments are equal to each other, but then the actual geometric figure itself, we would say, if they're the same size, right, we would say they're congruent to each other. So these properties here, okay, we already looked at these properties for equality, right, reflective, symmetric, and transitive. So if I have some segment AB, right, if I'm talking about the properties of congruence, I can say that that segment is congruent to itself. Okay. I guess I should make another note. If I'm just talking about the length of a segment, I do not put the line over top of it. If I'm talking about the segment itself, I do put the line over top of it. Okay, that's how we notationally determine what we're talking about. So length, no line over top. The geometric figure of a segment, we do put the line over the top. Okay. So the reflexive property, we can just say a segment is congruent to itself. The symmetric property, okay, I can flip things across a congruent symbol. So if AB is congruent to CD, then I can say CD is congruent to AB. And then the transitive property, right, if two things are congruent to the same thing, so we can say AB is congruent to CD, and CD is congruent to EF. So both AB and EF are congruent to CD in this case. We can say AB is congruent to EF. And again, we looked at that idea with equality last week, right, when we were solving equations. Questions so far? Everybody another second to copy stuff down. All right, so we've got a couple of definitions that we are going to use then. All right, so first, our definition of congruence. Okay, I can say that segments are congruent if and only if they have the same measure. Okay, so I can say if two segments are congruent to each other, then their lengths are equal. Okay, so this is the notation we would use, right? If the segments themselves are congruent, putting the lines over top, then their lengths are equal. And then we can also say that in reverse. If their lengths are equal, then the segments are congruent. Then our definition of a midpoint. Okay, we've worked with midpoint a lot already. Okay, it says the midpoint of a segment divides the segment into two equal or congruent parts. So if M is the midpoint of AB, and so just visually we're saying we've got some segment where M is exactly in between A and B. Well, then I can claim that AM is congruent to MB. Okay, if I know that M is the midpoint, I can say those two halves of the segment are congruent to each other. All right, and then our last postulate on the front here, the segment addition postulate. Okay, we've already worked with this at the beginning of chapter 1, but now we're going to use it to prove things. Okay, so if I know that A, B, and C are collinear, and B is between A and C, I don't know where, I just know it's somewhere between A and C, well, then I can say the length of AB plus the length of BC is equal to the length of the whole thing, AC. And we worked with that, I think that was the very first section of the book, but now we're going to use it in our proofs. Any questions so far on these postulates and definitions and properties? All right, then we're going to just take a few minutes here. When should you? That's your question. When should you start taking? I only took it twice in high school. I took it once my junior year and once my senior year. All right, take a look up here. Here are some answers for each of these. Okay, how did we do? Yes. Number 5, equality.
Okay, that's what I thought.
Yeah. Eight. Yeah. So which of these do we want to take a closer look at here? All of them? 8? Sure. So on number 8, they start with AB plus CD equals EF plus CD, and then they end up with just AB equals EF. So to get from here to here, what they did was subtract CD from both sides of the equation. Okay, so you always want to say, well, if I'm starting here, what do I have to do to get to here? Right, so there would be subtract CD from both sides. Which other ones?
Number 10.
Number 10? So this one is just kind of going in reverse for our definition of midpoint. Right? Usually we said, well, if we know that P is the midpoint of Ln, then LP equals Pn. But here we're just stating that in reverse, right? They're saying if I've got two segments that are equal to each other, and these points are all on the same line, then P is the midpoint, right? So visually we're saying, well, I've got two segments, right? LP and PN, and I know those segments have the same length, right? And remember, notationally, we talked about this a little bit. If I put the same number of hash marks on segments, that means they have the same length, okay? And they're all on one line. Then P has to be the midpoint. That's just our definition of a midpoint. What else? Yeah, so transitive property just says if I have two things that are either equal or congruent to the same thing. So on this one, I'm saying that FG is congruent to HI, and then also JK is congruent to HI, right? They're both, I guess I should have underlined HI, right? They're both congruent to HI, plus, therefore they would be congruent to each other, right? Like if I say, I'm the same height as Katie, and Katie's the same height as Ashley, then I'm the same height as Ashley. Even though that's not really true at all. Alright. What else? Any other ones we want to take a look at? Alright. Then let's start taking a look at actually putting these into proofs. Yeah, zoom out a little bit. What's that? Yeah, yep, that will still be the same thing. Yeah, that was going to be my first question. Marissa already answered my first question. The first line of every proof that we're going to look at is given, right? So, and that's literally written as given, right? E is the midpoint of DF. So that's going to be the first line of my proof. And the reason is just given. Okay? Well, so now what we have to think about is how did we get from one line to the next? Just like we did with the algebraic proofs. Okay, but now we're going to be using these different properties and postulates and definitions. So if I know that E is the midpoint of DF, how then can I claim that DE is equal to EF? Definition of a midpoint, right? Our definition of a midpoint is just if I have a midpoint, then the two halves of the segment that are created have to be equal. So now, from this line to this line, right, we started with DE equals EF, and now they're saying DE plus DE equals DE plus EF. How can we claim that? Yeah, we're just adding the same thing to both sides, right? I'm adding DE to both sides of this equation. So that's just going to be the addition property of equality. Okay, so now we went from DE plus DE equals DE plus EF to 2DE equals DE plus EF. So multiplication property is only if I'm multiplying both sides of the equation by the same thing, right? We didn't look at enough examples of this. I just kind of briefly mentioned it, but this is just combining like terms, right? It's only addition or subtraction or multiplication or division property if I'm doing that to both sides of the equation, right? We can just put combine like terms as a step, okay? And that's all we did here, right? This side of the equation didn't change at all. All I did was add these two together, right? If this was x plus x, I said that's the same as 2x, okay? So here we can just say combine like terms. Well, now we're claiming that DE plus EF equals DF. How can I claim that? So this one is a little bit trickier because this one actually doesn't directly follow from line 4. Katie?
Given.
Nah.
Segment addition.
This one's going to be the segment addition postulate. Okay, so if we look at this, okay, just looking from this line to this line, okay, well, we've got DE plus EF and DE plus EF, and then I don't really see any immediate way to claim that 2DE has to be the same as DF. So in this case, I actually have to go back to the diagram and say, well, if I look at the diagram, DE plus EF equals DF, the whole thing. That's our segment addition postulate, right? Just saying the addition of two pieces make up the whole. Okay, now this one, okay, the final line here. Okay, and remember, the final line is always what we want to prove. Right? So it says prove 2DE equals DF. So that's our final line.
Prove it.
Proof end.
That's our proof end.
It's not going to be definition of a midpoint. We could use substitution. That would be one way. There's actually two different ways that we could prove this at the end. Substitution is one of them. Because what we're saying is, well, we did have DE plus EF equals DF, and then somehow this changed to 2DE. Well, in line 4, we said those two things are equal to each other, right? 2DE is equal to DE plus EF, so I can substitute them in place of one another. Okay, that's one of the reasons we can use. There's actually another one.
Symmetric property.
Not symmetric property. It's going to be transitive, okay? Because we're saying two things are equal to the same thing, right? So up here, we're saying 2DE is equal to DE plus EF. And down here, DF equals that same thing. Therefore, these two things would have to be equal to each other. Okay, so when you're actually writing a proof, okay, you don't need to put both reasons, okay? But most of the time, substitution and transitive property are interchangeable. That's not 100% true, okay, but most of the time, substitution or transitive property are interchangeable. Okay? Feel okay so far? I think we've got time to do one more together here. So let's take a look at the next one. There you go. So hopefully we can at least get the first one, right, without even thinking. Okay, first line is always the given information. Now, it's also a good idea to mark things on a diagram, right? So if I'm given that KL and LN are congruent, I'm going to mark that. I'm going to say, well, same number of tick marks on those two lines. Then I'm also given that LM and LN are congruent. Well, so I already put one tick mark here, so these two segments are also congruent. Right, so let's start looking through this proof here. Okay, if I know these two sets of segments are congruent, how then can I claim that their lengths are equal to each other? Not symmetric. Yeah, this is the definition of congruence. Right? If I'm saying two segments are congruent, then I can say their lengths are equal. That's the definition of congruence. How then can I claim that KL is equal to LN? Yeah, so this is the same idea as our last line of the last one, right? We either use substitution or transitive property here. Okay? Well, then if I know that KL and LM have the same length, how then can I claim that L is the midpoint of KM? Definition of midpoint. Any questions on proofs so far? No homework tonight. Okay? We will continue this lesson